All right, so the next problem we want to do is problem 31 from chapter 12. A non-uniform bar is suspended at rest in a horizontal position by two massless cords. One cord makes the angle that 36.9 degrees with the vertical. The other makes the angle 53.1 degrees with the vertical. If the length of the bar is 6.1 meters, compute the distance x from the left end of the bar to its center of mass. Okay, so in other words, you want to find what is the center of mass on this bar because it's not uniform. The bar is not uniform, which means that the center of mass is not at the center; it's somewhere off the center. And you want to find, based on this configuration, the information you're given, what is the center of mass? Okay, so let's look at this diagram. This one has a mass, although the mass is not given. The bar has a mass. Let's just say is m, so it has a weight that's mg. On this end, there is a cord, so that's a tension. So let's call that tension as T1. And on the right-hand side, there's another tension that's called T2. And everything has to be balanced again. So net force in the vertical and horizontal has to be 0, and net torque also has to be 0, because you're asked to find this distance. So you have to use a net torque equals to 0 whenever distance is involved. So that's a net force. This T1 has this component, positive y component, and the negative x component. On this side, you have positive y component and the negative and the positive y x component. So these two has to be balanced each other. These two have to be balanced each other, and these two, when you add it together, has to be balanced by the weight of the bar. So let's do that. So that's horizontally, that's T2. So you have your T2. If this is angle phi, then this is your angle phi. So the T2 has a horizontal component that's opposite the angle. So you have T2 sine phi, okay? And that has to be equal to T1. Again, this angle theta. So this is opposite. So T1 sine theta, okay? Angles are given, so you can basically find out the ratio. Okay, so you have your T1, so you plug in the numbers for the angle. So your T1 basically, your T1 is equal to sine 53.1 over sine 36.9 and then times T2. So your T1 is equal to 1.33 T2. Okay, so that's based on information that the horizontal component cancel each other. Now, in the vertical, you have your T1, you have a T1 cosine theta plus your T2 cosine phi, and then minus mg. The whole thing is equal to 0. Okay. So what we can do is that if you look at this, we don't know about T1, we don't know about T2, but we do know that T1 and T2 they are related to each other. And then from you have T1, you have your T2 in this equation, and you have your m. All these are not given. So what you can do is plug in the numbers to these angles, and then just have the percentage with the numbers that you have, and then see what you get. So here we can actually express our mg, the weight of the bar, in terms of this expression. So you have your mg, that's equal to T1, and then cosine 36.9, and then plus T2 cosine 53.1. And realizing that your T1 is equal to 1.33 T2. So we're going to replace our T1 with that expression. So altogether, your mg can be expressed in relation to T2. Your mg is equal to 1.664 T2. Okay? So we have all this. But so why are we doing this? Because first of all, you need to figure out how these forces are in relation to each other before you can use the net torque equals to 0. Because when you're dealing with net torque, you still have to deal with T1, you still have to deal with T2, and so forth. All right, so now we want to calculate torque. I mean, after you apply Newton's law, you find that this is as much you can get. You can't get any further information based on Newton's law. So now we're ready to use the net torque equals to 0. Okay, so you have to pick a point to find to calculate torque about that point. And I'm going to pick this one. Okay, so when you pick this point as your as a reference point to calculate torque about that point. Then you can see that your T1 is directly applied at this point. So T1 does not contribute to torque. So that makes the calculation a bit easier. And that is why we express everything in terms of T2, because you do need T2 information. But then when you use the net torque equals to 0 applied at that point, you don't need to have the information of T1. Okay? So now let's do net torque. That's equal to 0. The first term, of course, is your weight and its separation. The distance, the moment on, so you have your x, and then times your mg. So that's your R cross F. What about the sign? So this is the applied force, and your R, draw the extension. This is your R, so R cross F. So R cross F, you can see that it produces a negative 10. So put a negative sign in front of it to indicate that's a negative 10. So this is the torque produced by this gravity that's going to be negative. And then the other force that will produce the torque is T2. So you have your T2, so the radius is your total length of the bar. So you have the L, you have your T2, and then because it's applied at angles, you have to use R cross F, that's RF sine theta. So sine of the angle between them. What is the angle between them? This is the radius. This is the radius, and this is the T. So the angle here will be 90 minus the angle you're given. So sine of 90 minus V. Okay? And what about its sign? Is it positive or negative? So you have your R. You have your R. Sweep across the, sweep your finger, toward the second vector. You find that it produces a positive torque. So put a positive sign in front of it, and the whole thing here is equal to 0. Okay? So now we can actually find what our x is, because that's what you're going to find. So your x would just be, if you move this to the other side of the equation and divide the mg on both sides, then you have LT2 and then sine of 90 minus 53. What would that be? 90 minus 53, that would be 36.9. And then over your mg. Okay? So now we're ready to replace our mg. So our mg is this one. So you have your L. L is 6.1. And then you have your T2. You have your sine of 36.9. And your mg is 1.664 T2. So you can see that T2 basically cancel. You don't even need that. So after you do the numerical calculation, you find that your x is about 2.199 meters. Okay, so the central mass of this bar is located not at the center, it's actually at 2.199 meters. Okay, so that's problem 31. And the next one we're going to do is 59. All right, so let's look at this problem. 59. In this diagram, the mass of the bucket is given 817 kilogram. So an 870 kilogram construction bucket is suspended by a cable A that is attached at point O to two other cables B and C, making the angle theta 1 here. So the theta 1 here is 51 degrees, and theta 2, this is your theta 2, which is 66 degrees. With the horizontal, find the tensions in cable ABC. And in the problem, it says that to avoid solving two equations in two unknowns, position the axis as shown in the figure. But I found that it's actually, if you rotate your axis, that's actually quite, it's not that straightforward or intuitive. We might as well just, resolve this vector into our regular Cartesian coordinate, the x and y axis. So you still have your horizontal here and you still have your vertical here, so that, it's not, I don't think that will be too difficult to do that. So that just use our own, by usual way, resolve the vector into the x and y, according to this diagram. So again, the whole thing is 0. Not the whole thing is 0, but the whole thing is balanced, which means that the net force acting on this part, acting on this system has to be 0. So we draw a free body diagram. So this is the point where we look at all the forces acting at that point. So you have the downward force, you have this tension, you have that tension, and regarding the block, we know that the weight of the block should be balanced by this tension. So that's how we relate the weight of the block and the tension. And all these three forces have to be balanced each other, because that point is stationary. Okay. So now, this is just regular, resolve the vector into x and y and sum all the x components together and set equal to 0. Sum all the y components together and set equal to 0. So that's as simple as that. So it's not that difficult. So let's do that. So you have your, so the T2, the TC has the positive x component and a positive y component. And TB has a negative x component and positive y component, and this two positive y components is going to be balanced by this downward tension. So let's set out the equation according to this diagram. So you have your TC, okay, and then times cosine theta 2, that's your x component, that minus TB, and then cosine theta 1. The whole thing is equal to 0. And TC and TB, right now they are unknown, but theta and theta 1 and theta 2 are given. So you can actually calculate. You can calculate, calculate the force magnitude in relation to each other. So you have your TC. That's equal to cosine theta 1, cosine 51 over cosine 66, and then times TB. So your TC is equal to 1.55 TB. Okay? So let's keep it at that, because you have one equation but two unknown. Now that's utilizing information in the vertical direction. In the vertical, you have TC sine theta 2 plus TB sine theta 1. That has to be balanced by TA. So you have TC sine theta 1, TC sine theta 2 plus TB sine theta 1, and that has to, and then minus TA. That has to be equal to 0. Okay, and we also know that if you draw a free body diagram for this plot, this is the mg, and that has to be balanced by TA. So that's how you find your TA. So your TA is just mg, which is the known value. So m is, this is your mass, and then times 9.8. So your TA has a magnitude of 8,006.6 Newton. So you have that, and then so we can plug into this equation. So you have your TC, and then sine theta 2, which is 66, and then plus TB sine theta 1, which is 51, and that's equal to 8,006.6. Okay, and then we can utilize this information that TC is equal to 1.55 TB and do substitution. So your TC here is replaced by 1.55 TB. So 1.55 times sine of 66, and then times TB, and then plus sine 51 times TB. And the whole thing is equal to this. So you can see that now we have one equation, one unknown. So you can calculate your TB. So your TB, after you plug in to the calculator, you got your TB, that's 3,673 Newton. So once you have your TB, then plug into this equation, then you can calculate your TC, and you should have 5,693 Newton. Okay? So basically, you can see that to do this problem, you don't really have to rotate your axis. You can just directly resolve this vector into the traditional x and y axis, and then sum up all the forces in the horizontal, set equals to 0. Sum up all the forces in the vertical, and set equals to 0. And then the rest would just be substitution and finding how much force is equal to in relation to other forces. Okay, so that's your 59. And the last problem from chapter 12 is that we want to do is 61. So let me just draw the diagram first. All right, so problem 61. A force F in this diagram keeps the block, which has a mass that's 6.4 kilograms, and the pulley is in equilibrium. So the whole thing is in equilibrium. The pulleys have negligible mass and friction. Calculate the tension in the upper cable. So the cable. So it will be like this. So you'll also find the tension up, on the very top. And let's see. When the cable wraps halfway around the pulley, as here, the magnitude of its net force on the pulley strikes the tension in the cable. Okay, so that's a clue. The whole thing is balanced. You have this block that has a weight. If you did not apply this force, the whole thing, of course, is going to move down. But because you apply this force, it's kind of like keep it up. Okay, so how much tension is actually, is right here. So let's see. If you apply a force right here, so you have the force here, so that's your force here, and then this will also have the same amount of force here because it's the same rope. If that's the same rope, which means that they have to have the same tension. This is the tension. The tension is basically balanced by, the tension is provided by this force. So this is your F here, and that's your F here. Okay. So you can see that at this point, this force has to be balanced by this too, because everything is balanced. This is 1F. This is 1F. So at this point, this tension at this point should have 2F, and that's upward. Okay. Now, when you look at this side, you have this. If this is 2F, that's upward, which means that the tension here has to be 2F. That's pointing in that direction, and so the tensions here also has to be 2F. So in that case, you have 2 and 2, which means that the tensions right here to keep the whole thing balanced should be 2F plus 2F. That's your 4F, right? And so that by the same analogy, this is 4F, which means that your 4F has to be in this direction. You have another 4F that's also in that direction. So altogether, how many F's are there for the tension? So tension should be 4 plus 4F. So altogether, your tension has to be 8 times the magnitude of force. How much is the force then? If you look at this block has how many forces acting on it? You have 4F, you had 2F, and you have 1F. So when you add this 3 together, that has to be balanced by gravity. So you have 4F plus 2F plus 1F, and that has to be equal to mg. So this, you can calculate your force magnitude F. So that will be mg over 7. Okay, so then you plug into this equation, you can calculate your tension. Your tension would just be A over 7 times mg. And m is given, g is 9.8, so when you plug in a number, you should get 71.7 Newton. Okay, so that's a kind of neat way to see, how much forces that needs to be balanced. What is the force that you have to apply so that whole thing keep balanced? This is the tension, so you have, if this is 1F, this has the same amount of F. This is 2F, that's 2F, 4F, and 4F, and so forth. And the tension is the sum of these two forces. Okay? So that is that.